Hello, this is Miraj Patel, and today we're going to be talking about solving kinematics problems and graphical analysis. And this is the second video of the kinematics unit, and let's begin. So, uh, before we solve any problem, let's talk about some strategies to solve them. So the most important part, if you want to solve problems pretty quickly, is just be familiar with your equations. If your teacher doesn't allow you to use the equations on the test, it is to your benefit to know your equations. Like for my class, it was an AP class, and even though we have a formula sheet, our teacher made us memorize the kinematics formulas, and yet I still know them, and if you know them, they'll be really helpful to solve problems because you'll know it right off the back instead of searching on a formula sheet that you might not be familiar with. So just know your equations or be familiar with them. And when reading the problem, like in every class, you should always extract the important information because these problems are going to tend to be word problems. So it's always important to extract information that is important. So list the variables you have, and to solve a kinematics problem, you need to know about 3 variables. So the magic number to solve a kinematics problem is 3. List what variables you need to solve for and find the right equation. So then you have to, so after listing the variables you have, list usually the one variable that you need and find the right equation that has all 4 variables and where it can easily solve for the unknown variable. And then always then solve for the variable with using the equation you picked, and always give units. So it's always important to give units. So your teacher might often, take off a point or two because you don't write units, and especially if you're taking like the AP exam, it's always important to impress the readers by writing what units your answer is in. I mean, sometimes they might even give a point off of the unit. So just always write your units. It's a good habit to have. And so if you're just beginning to solve problems, you should really copy this chart. This chart is really helpful when you're learning how to solve these problems because it sort of like lists the information you have on the in each equation. Sorry about that. So here we have our 4 formulas. So we have the acceleration formula. Then we have the average velocity equation. Sorry, again, that should be a plus sign. Then we have the Galileo's formula right here. So, and then we have energy formula. And so basically all of them have initial velocity, but acceleration doesn't have displacement, average velocity doesn't have acceleration, Galileo's does not have final velocity, and energy does not have time. So these are the variables that aren't in these equations. And so have this by your side when you're solving like the first few problems, and try to cover this up and try to figure out to pick a formula by yourself without looking at this eventually as you solve more and more problems. So here is our first problem. A car is traveling at 30 meters per second and it slows down to 20 meters per second in 2 seconds. What is the acceleration of the car? Or what acceleration did the car experience, it should say. So we first write down our givens. So we pick out the numbers that we have, and so 30 meters per second is definitely important, and that's the initial velocity, so v sub I. Then we have time, 2 seconds, and we have final velocity, v sub f, at 20 meters per second. So we wrote our given, so the next step is write your unknown. So, uh, so the unknown in this case is acceleration, because it asks us in the problem what is acceleration. So unknown is acceleration, and just on the side I wrote the units for acceleration, so when we get our final answer we know what to put, which is meters per second squared. And so basically we should pick an equation that has all four of these variables, so pretty much it doesn't have displacement. So if you go back to our sheet here, the formula doesn't have displacement, is acceleration. So we should use that formula and plug in what we have and solve for acceleration, which is pretty easy because acceleration is already solved for. So if we do 20 minus 30 divided by 2, it's negative 5 meters per second squared, and the negative just means that it's in the opposite direction of the motion. So, and this makes sense because the car slowed down. So remember when we were talking about in the original video that if acceleration and velocity are in opposite directions, then it's negative, the acceleration, so that means it's slowing down. So this should actually be a negative sign, but sometimes you just have to tell them that it's slowing down if instead of putting a negative sign. So that's a good important thing to do. So important type of problem in kinematics are free fall problems. So free fall problems are when an object in a scenario is only affected by gravity. And so obviously these skydivers are only affected by gravity because gravity is pulling down. And believe it or not, the only force that's acting on the moon is gravity. So we'll talk about that later on in this line of videos. And so these problems always have these certain characteristics, and it's important to remember or think about them when solving these problems. For one thing, the acceleration is always approximately 10 meters per second squared. So the acceleration is of gravity is really 9.8, but to keep it simple, we just round it to 10. So in certain classes, you can just call it 10 meters per second squared. So ask your teacher. But the gravity is the only acceleration on any object in free fall. So it's always 10 meters per second squared. The instantaneous velocity at the top is always 0 meters per second in the vertical direction. So basically it's saying the velocity at the very top of the trajectory when you're throwing it straight up is always 0. So like if you throw up a ball, it's moving up, it stops at the top and moves down. So because it was moving up and then it comes back to your hand moving down, it had to pass through 0 somewhere, and 0 is where it's at the top of its trajectory. So, and I mean, you can even see it when you throw up an object. It always stops at the top of the trajectory. And then a cool thing about objects being thrown up and coming back down is the velocity you throw the ball or object up with equals the velocity it lands with. And this has to do with gravity being a conservative force. So a conservative force means it gives back what it takes. So like gravity, if you throw something against it, it comes back down to you, but it comes with the same velocity you gave it. So it's kind of cool. And another force commonly known as a conservative force is a spring, because if you push or pull a spring, it will give back the force you gave it, but in the opposite direction. So gravity is opposing your force, but it gives back what it takes. So if you throw an object up, it comes back to you with the same velocity. If gravity wasn't conservative, like friction isn't conservative because it just takes away your energy or force without giving it back. So gravity, if it wasn't conservative, it would just take away your speed, but without giving any. But gravity is conservative, so it will give back what it takes. So here is our second problem, and this is a free fall problem. So you throw a ball 15 meters per second straight up into the air. How high did it go? Did the ball go? So imagine you're this person and you threw up a ball 15 meters per second. How high did it go? So this doesn't seem like a long problem, but you can actually pull out three variables from this. So the first thing you know from the problem is you threw the ball 15 meters per second up. So what is that? Is that velocity, acceleration, displacement, time, final velocity? So 15 meters per second is actually the initial velocity because that's what you start with. So you call the start of the throw the initial condition. So 15 meters per second is going to be initial velocity. And for free fall, you know that acceleration is always gravity, which is 10 meters per second squared. So that's your second piece of information. And now we need a third piece of information. So remember what I told you. So if you throw something up, it has to stop at the top. So because it goes from a positive direction, so an upward direction, to a downward direction. So it had to stop somewhere, and that happens to be the top. So there are your three pieces of information. The acceleration is negative 10 meters per second squared. Sorry, I forgot to mention gravity, because it's downward, you have to call it negative 10 meters per second squared, assuming that up is positive. Initial velocity is 15 because you started with that speed. And final velocity is 0 because we're calling the top of the trajectory 0. So it's important to know your perspective when you're solving these problems, because you could have called the initial velocity the top, which would be 0, and the final velocity negative 15. So you could have switched these and you could have gotten the same information or same result. But you can call whatever part of the problem, whatever you want, as long as you stay consistent with it. But it's always good to call, like in free fall and you're trying to find the height, call the initial velocity whatever you threw it at, and then the final is 0 at the top. So it's important to know your frame of perspective, or your perspective. So unknown, we want to find the height, which is a distance, which means we want to find displacement. So the formula I would use is the energy formula, because we have final velocity, initial velocity, acceleration, but we don't have displacement. So we plug in all the information we know and move everything to the other side. So we get that, and then we subtract 225 from the other side, and then divide by negative 20, and we get 11.25 meters. 11.25 meters. Sorry, I forgot the units, but I wrote it right here, so I would just draw an arrow there. So basically, you threw up the ball, and at 15 meters per second, 15 meters per second, and it went up 11.25 meters. So this is what I'm talking about. Something that you can do every day, where in everyday life you can calculate something through kinematics. So you probably can't measure the initial velocity, but you could measure like the time you threw up a ball, like the time it took to land in your hand after you threw it. So this is an example of a problem that you can easily solve in your backyard. So just throw up a ball, time it, you know the acceleration and you know the final velocity at the top, and you know the time it took. So so this is an easy problem you could solve at your house. So, the second part of today's video is we're going to talk about some kinematics graphs. So, we talked a little bit about it in the first video, but here we're going to go to in-depth about the graphs. So, graphs are important to understand in physics because they express a lot of information about a situation. So, from this graph, we have to make an acceleration versus time graph and figure out the acceleration of the object experiences between 2 to 3 seconds, and we want to figure out the overall displacement. So we're going to have to make two other graphs to solve this problem that I made. So, and this is the graph that I give you. So we have a velocity versus time graph. Velocity is meters per second, time in seconds. That's all good. So acceleration graph. So acceleration versus time graph. We have to analyze the slope of each segment. So if we go back to this graph here, we have four different slopes here. So we have four different segments. They all have their same slope. So we have to, different slopes. So we have to analyze each segment's slope to do this graph. And if you're taking AP Physics 1 or an algebra-based physics class, this acceleration versus time graph should only have horizontal lines because we in algebra-based physics class we require acceleration to be constant. Otherwise, we have to use calculus. And so, from this particular graph, if we analyze the slopes at all these segments, so we do rise over run, so 2 over 1, what's the slope? 2, because it's positive, and it's 2 over 1. The slope here is obviously 0, because it doesn't rise anything, so 0 over 2 is 0. This little segment here is 1, 2, 3, 4, 4, so rise, so negative 4 over 1, because 1 second difference. So negative 4 is the slope of this, and then the slope of this part is rise over run, so it didn't rise at all, so 0 over 1 is 0. So basically, if we plot this on a graph, we should get this. So acceleration is meters per second squared. So from 0 to 1 second, it's accelerating 2 meters per second in the positive direction. From 1 to 2 seconds, it wasn't accelerating at all. Constant velocity, no rate of change. From 2 to 3, the rate of change of the velocity was double the first one, but in the opposite direction, so slowing down. And then from 3 to 4, it did not change at all. So acceleration versus time graphs are pretty straightforward. You just analyze the slopes of each segment and plot it on a line. And they should always be horizontal if you're in an algebra-based physics class. Displacement versus time graphs are a little more tricky because they have some curves. So basically the first step is find displacements at critical points. So this means all the segments with different accelerations and then the x-intercept. So whenever the velocity versus time graph crosses the x-axis, you have to plot that point. So that's a critical point. So plot these points first. So once you find the displacement versus, the displacement of the velocity versus time graphs, which is just the area between the line and the x-axis. If after you find the areas at those points, you plot them. If the velocity was constant, you connect them with a straight line. And then if we for the graphs that are having accelerations, we have to use this chart here that I made, and I'll explain it in just a second. And I mentioned this earlier. This graph is the only graph that in an algebra-based physics class that will have curves in the realm of kinematics. So in kinematics, this is the only graph that you should see curves. So here, I show you the graph here with displacement, and here's the original graph. So basically, I did the calculations here. So I found the area under every segment. So at 0, it's pretty obvious. The displacement is going to be 0 because it's not even moving at all. After 1 second here, this is a triangle, so 1/2 base times height. So 1 times 2 times 1/2 is 1 meter. So this object moved 1 meter. So I would plot that point, and since it was accelerating, so it's going faster and faster and faster. As it moves faster and faster, the displacement between all like 2 points of the same gets greater and greater because it's moving faster and faster. And you remember how the graph of displacement versus time for like an accelerating object gets bigger and bigger, so it curves steeper and steeper, just like this. So it's accelerating in the forward direction, it curves upward. And so at 1 second to 2 seconds, the area is just a rectangle. So 1 times 2 is 1 times 2 is just 2. And then if you just add that with the previous displacement, you get a total displacement of 3 meters. So we're all the way at 3 meters at 2 seconds, and I connected with a straight line because there's no acceleration. So it's a constant change. Then at 2 to 2.5 meters per second, 2 to 2.5 seconds, the car is, or the person, whatever, is slowing down because the velocity is decreasing, but they're still moving forward. So we find the area. So 1/2 times 2 times 1/2, the area of a triangle right here, plus 3. So 3 was the displacement before here. Gives us 3.5. So I graph that 3.5, plot. Then I draw upward curve because the object is slowing down, so it's not as moving as rapidly, so it's gonna slow down and have an upward curve like this. Then now it's at a critical point because it stops moving forward, and now the area is negative, so it's gonna start moving backwards. Okay, so this object's moving backwards. So now the displacement's going to be going down. So it's the same exact curve because these areas are symmetrical, but it's exactly opposite because it's slowing down, going backwards, so it's going to speed up in the negative direction. So speeding up, speeding up, speeding up, more displacement. Then from 3 to 4, it's just a, another rectangle, and it's basically symmetrical with this rectangle here. So, so basically, it's -2 times 1/2 times 1/2, which was the curve, and then -2 times 1, because 1 times -2 gives us, and we subtract this from 3, we get 1. So we're all the way back here at 1. So if we go back to my so if we go back to this little chart here, positive acceleration and speeding up, so it's speeding up in the positive direction, it's going to look somewhat like this, because it's going faster, faster, more displacement. But if it's moving forward but slowing down, it's still going to climb upwards like this, but it's going to be slowing down, so less displacement, less displacement. Now, thinking about going backwards, positive or negative acceleration, positive acceleration but moving, slowing down in the negative direction, so it's going down, but it's slowing down, so it's not moving as fast, so it's going to be slowing down in the negative direction, so it's not going to be moving as steep, so it's like the flip side of the one right above it. So this is just moving negative direction. Now this is just like the top one, but except it's going in the negative direction, so it's moving faster and faster, greater and greater displacement, just like you can see here. So if we skip over these graphs like we talked about, basically, if I had to explain this object from 1 to 2 or 0 to 1 seconds is accelerating pretty quickly, 2 meters per second squared, because that's the slope of this. Then from 1 to 2, it's not accelerating, going constant speed, and after 2 seconds, it's moved 3 meters away from the original point. Now, it starts slowing down here, but very fast. So it's 4 meters per second squared, because that's acceleration slope. Now, after 0, it's 3.5 meters away, starts going backwards. So hence this downward curve here. It just moved a little backwards. Now it's moving backwards at 2 meters per second square, 2 meters per second for 1 second. So this pretty much equals, counters this movement. And so to answer the question, the acceleration between 2 to 3 seconds is -4, because it's going opposite of the movement, and 4 meters per second because the slope rise over run, so -4 over 1. And then the net displacement, as we can see on our graph, so initial and then final. So final is 1 meter, initial was 0, so final minus initial, 1 minus 0 is 0. So to answer the question, the problem stated, the object moved 1 meter in the positive direction, and the acceleration between 2 to 3 seconds was -4 meters per second squared. Thank you for listening to my physics video. Today we learned how to solve one-dimensional kinematics problems, and tune into next week's video about how to solve projectile motion kinematics problems. So these problems actually have 2 dimensions, an x and y component, and it seems very complicated, but trust me, you can tackle this. We can do it. Please, if you enjoyed this video, Please tell your friends, family members, people who you know that are taking physics, and please like this video. And email me if you have any questions. I know physics can sometimes be super hard to understand, especially when I was first learning it. I was honestly confused about all these formulas and um, the terminology and all these, like how my physics teacher could do it in his head. But if you keep on trying, I'm sure you will understand it. So keep on playing the video, ask your physics teacher questions, and you can email me at my my email, mpatelbuccaneer@gmail. And if you need help or if you know anyone taking chemistry, please visit my website for chemistry, buccaneerchemistry.weebly.com, for chemistry tutorials. Thank you and have a good day, and I hope to see you later.